In this lesson, we will explore various optimization techniques to keep our Postgres databases fast and efficient. Before we get technical, let's consider what performance means to us in the context of computing. According to the Oxford English Dictionary, performance can be defined as an action, task, or operation seen in terms of how successfully it was performed. That makes sense. We want to store and process data in the most successful way. But let's consider, what does success mean to us and how do we define success? In computing, we have three primary concerns. The first is correctness, the second is speed, and the third is efficient memory usage. And they are generally prioritized in that order. Consider how these will apply to databases. For correctness, we need to ensure that our SQL operations are reliably doing what they need to do. For speed, we want SQL queries and mutations to return results as quickly as possible. For memory usage, we want to minimize the space used for the data stored at rest as well as the working memory used to process our queries. You may recall learning about Big O notation in Python fundamentals as a way to examine algorithmic complexity. When it comes to optimizing databases, the internal algorithms and data structures used by Postgres to compose query results are what we are interested in examining. Now that we've defined our goals, let's take a look at some techniques to help us get there. An important choice to make when creating a database table is the data type of each column. We've mostly worked with the regular integer type, but you may not be aware of all the options for storing numeric data. This table lists some of the supported data types, along with their size and the range of values each size allows. For example, let's say you are certain that a given column will never have a value greater than 32,767. Then, you can use half the memory you would otherwise use by switching from a regular integer type to a small int type. That's a big savings afforded to us by simply eliminating space that would have been wasted. By using smaller types, we also improve the speed of reading and writing these values. The same principle applies to other data types such as those that are text-based. You are welcome to explore those, but we won't cover them now for the sake of time. One of the reasons we spend so much time on data modeling in week 1 is that having the right database design up front is key to high performance. Recall the concept of normalization. Entities should separate concerns in a way that reduces redundant data. The week 4 database is a perfect example of a non-normalized database. In fact, let's write a query to see how many redundant artist names are present in the MOMA_works table. We can do this by calculating the difference of the number of artist values in the table and the number of unique artist values in the table. As you can see, we have 124,466 redundant artist values. That's a lot of redundant data. We can also take a look at the top offenders using the query shown. For example, we can see that Pablo Picasso's name is stored over 1,300 times. That means if we ever want to update his name, we would need to update over 1,300 records, as opposed to one in a normalized model. A normalized model would leverage foreign keys to relate a work to an artist, instead of having each work store its own artist column. There is a benefit here, however, and that is that by keeping the data unnormalized, we don't incur the cost of performing a join operation when querying for related records. The benefit in this case is likely not justified. However, if you are regularly joining across a dozen tables for certain queries, an unnormalized structure may be warranted. Joins are quite an expensive operation relative to other query operations. Another strategy for improving a database query's speed is to see if its complexity can be reduced. With all of the tools that Postgres provides, it can be easy to find yourself reaching for the wrong one. For example, say you have a customer ID value of 12, and you're interested in finding out whether this customer has any orders. Remember, a customers to orders relationship is a classic example of a one-to-many relationship. That means one customer can have many orders, but each order can only belong to one customer. Let's take a look at one approach. This query works. With this, we are counting the number of records in a join between orders and customers for a customer ID of 12. And then we are checking for counts that are greater than 0. But hang on, if the orders table already has a customers underscore ID column, then why do we need to involve the customers table at all? Let's try this again. Here we have a similar approach in which we still filter the customer IDs, but we eliminate the need for a join by using a subquery. But wait, why are we counting anything when we just want a yes or no answer? We don't need to know if the count is higher than 0, we just want to know if any orders exist at all where the customer ID is 12. This is a good use case for the exists function. Despite each of these queries providing the correct answer, this is the optimal query for the given task. We get to the same place with each query, but this one requires the least work. We should also consider how we can reduce the number of round trips from client to server when writing queries. When working with a backend, queries and subsequent query results must be transmitted over the network. Unfortunately, there is an inherent latency that comes with network communication, and this latency is known as the round trip time. Minimizing the number of round trips is a good strategy for improving the efficiency of a query. For example, consider the effect of executing these 5 distinct insert statements back to back. What steps would need to take place? First, the database client would make a request to Postgres. Second, Postgres would evaluate the SQL statement, checking for syntax mistakes and parsing out the relevant table, column names, and values. Third, Postgres would perform the specified operation, an insert in this case. Fourth, Postgres would prepare a result, such as a success or failure notice. Fifth, Postgres would send that result back over the network to the client. And then the client would process the result from Postgres. Finally, we repeat steps 1 through 6 4 more times. In this example, we make all the inserts in one statement, so we can avoid step 7 altogether. Think about the previous example with 5 distinct select statements. If a failure occurs at any step along the way, care would have to be taken to track which statement failed in order to retry it. And you may accidentally end up with an undesirable set of partial data in the database. In this example, the statement is all or nothing. It either succeeds or it fails, and there is no opportunity for partial success or failure here. Unfortunately, ORMs have a pesky habit of enabling what is known as an N+1 query. The story goes like this. A developer is tasked with printing out the orders of each customer. Knowing this should be a simple task, they go ahead and write a nested for loop like so. They query for all the customers using the all method. Then, for each customer, they iterate through each of the customer's orders and print each order in turn. Initially, this works well. But as the number of customers grows, the database is inundated with queries and struggles to keep up. What went wrong? On the face of it, this code is straightforward. But what's not obvious is the query formation behind the scenes. It's true that the all method queries the customers table, but unfortunately the returned customer objects do not contain the corresponding orders. Therefore, the ORM is creating additional queries to get the order data for each customer. This is called an N+1 query, because the inner for loop runs n times, making n queries, in addition to the one query for customers' objects. The n in this case stands for the number of customers that were returned in the first query. As you can imagine, this is very inefficient and only gets worse as n grows in size. For example, if we had 100 customers, we would be hammering the database with 101 queries in a very short time frame. Now that we understand the problem, we can get this down to at most 2 queries using code that looks something like the following. Here we first get a list of all of the orders with a single select query. Then we get a list of all the customers with another select query. For each customer, we look for a corresponding order in the list of orders. Since we already have the list of all orders, we search through that instead of sending a new select query to the Postgres server for each order. This is a good example of why ORM magic can be tricky to use. Care must be taken to understand what is happening at the SQL level under the Python abstractions. Let's go over some final points before we wrap up. Like most software, a database will only perform as quickly as its slowest component. Go after the slowest bottlenecks first. Unless you are working on something that needs to be absolutely blazingly fast, micro-optimizations are simply not worth your time or effort. Avoid storing HTML, XML, JSON, or other markup languages in the database. Storing, retrieving, and displaying this data is expensive. Another good idea is to establish a data retention policy to clean up records that are obsoleted or outdated. These records might be outright deleted or archived in an external storage solution, such as a hard drive. Smaller tables means less storage use, less memory use, and less network bandwidth usage. Record lookup times will also be faster as the tables are more compact and quicker to search through. Finally, it's important to recognize that smart database modeling only goes so far. The query formation must also be thoughtful to reduce complexity, unnecessary round trips, and pitfalls like the N+1 anti-pattern.